Hello everyone, welcome to lecture 12 on the online course on modern display technologies, flat panel display. This lecture is on the fundamentals of liquid crystals. We will be continuing from the previous lecture. So, here is the lecture outline. Orientational order of liquid crystals. We will discuss about the orientational order parameters, then Landau-Dieguenis theory and also Mayer-Sope theory. Then we will look into the elastic properties of different types of liquid crystals like pneumatic, cholesteric and smectic liquid crystals. So, what is the orientational order of liquid crystals? So, the orientation is one of the important feature of the liquid crystals. So, if you consider the rod like molecules, they basically tend to align along a common average direction, just like here. Okay. So, that direction, that average direction is basically called the director, and that is typically represented as n cap. So, you can see that each of the molecules are not fully aligned to the same direction, they may be tilted this way or the other. So, in pneumatic liquid crystals, you will see molecules have orientational order, but not fully positional orders. Because of this kind of alignment, liquid crystals basically show anisotropic properties. The director n cap and minus n cap, they are physically equivalent in the case of a pneumatic liquid crystal, right. So, because it is symmetric. So, the orientational distribution function f theta phi basically describes the molecule's orientation in the space. So, this particular diagram shows you what are this theta and phi. So, theta is basically the polar angle that specifies the orientation of this axis vector a cap in the 3D space with respect to the z axis. Phi is basically the azimuthal angle that specifies the orientation of the projection of this vector in the xy plane. So, that is how you measure it from the x axis, that is basically the azimuthal angle phi. And what is this a cap? This is the unit vector that is along the long axis of the molecule. So, depending on the orientational order, there is a parameter that can describe how oriented your crystal is. So, the degree of alignment is basically measured by this order parameter, which is capital S. Okay. You will see that some of the symbols are like used for different purpose. So, never mind those. So, here you can see that because one is from the thermodynamics, this is from the liquid crystal jargon. So, they prefer to use this S. Okay. So, here you can see S is basically a scalar measure of orientational order that is obtained as a average value of the second Legendre polynomial. So, S is basically average of the second order Legendre polynomial P2 cos theta, which is half 3 cos square theta minus 1. So, once you do this, it is basically integration from 0 to pi half 3 cos square theta minus 1 f of theta sin theta d theta divided by 0 to pi integration of f theta sin theta d theta, right. So, what does it mean? When you have s equals 0, that is basically this case, that is telling you that there is no order at all. So, that basically corresponds to isotropic state with random orientation. Okay. Now, s equals 1 on the other extreme will tell you that there is perfect alignment of all the molecules with the director. So, that is s equals 1. So, anything in between like s equals plus 0.5 or minus 0.5, let us look into the minus 0.5 first. So, these are a special case when the molecules lie randomly in a plane which is basically perpendicular to the director. So, the director is in this direction. So, the molecules are basically lying in a orthogonal plane, that is in this kind of a plane, and there they can have any orientation, right. So, in case of real pneumatics, you will see S is typically positive and it is less than 1. So, it can be like this 0.5 where they are aligned towards the main director, okay, but there is some bit of randomness. So, now we can go to this Landau-Dieguenis theory. This basically explains the isotropic to pneumatic phase transition using the free energy expansion. So, the free energy density F can be expressed as a function of the order parameter S. So, now you see they are basically trying to relate the two domains of thermodynamics and this orientational ordering that you have seen for the liquid crystals. So, small f, which is basically the free energy density, that is related to half A T minus T star, okay, S square minus 1 by 3 B S cube plus 1 by 4 C s to the power 4 plus half L delta S square. Now, this small a, b, c, L, these are basically constants, and T star is basically the virtual second order phase transition temperature. Okay. Now, this quadratic, cubic and quartic, these terms control the phase stability. The cubic term here is important, okay, because isotropic nematic transition is basically first order. So, at the transition temperature, the order parameter changes discontinuously, and this theory also explains metastability, supercooling and superheating. So, what we expect that for uniform order, for a given temperature, the order parameter S is determined by minimizing the free energy. So, you have to obtain dou F by dou S. So, F and S are related like this, you do dou F by dou S, you get this expression A T minus T star into S minus B S square plus C s to the power 3 or S cube. So, that has to be equal to 0. Okay. So, if you take S common, you can get this. So, one solution is that your S is basically 0, that means it basically corresponds to a isotropic phase, which is nothing but random orientation of the molecules at high temperature. The other one can be from this, which is basically the solution 2, which is 1 over 2 c b plus square root of b square minus 4 a c into t minus t star. So, this basically corresponds to the nematic phase. So, here you get a global minimum at low temperature. There can be another solution, which is basically the minus term here. So, that is same, but you just have this negative term here. This corresponds to a local minimum in free energy. So, that gives a unstable state. So, isotropic to nematic phase transition, this happens at the critical transition temperature, where you have T and I. Okay. That temperature, the free energy of the isotropic phase, that is F1, and the nematic phase F2, these two free energies will be equal. So, equality of free energy that happens at T equals T and I. So, in that case you have this critical order parameter SC. So, what you can write that F2 at S2 equals SC will be equal to F1, and that is basically 0. Okay. So, you can go back to that equation, put your value of S2 equals SC, and you will see this is what you obtain. Okay. Now, what is the equilibrium condition for at T equals Ni, that is the critical transition temperature? You will see you can obtain this, okay, and by using this equation and the above equation, you can obtain what is the value of SC. So, from this only you can obtain what is SC. SC is 3A by B into T Ni minus T star, fine. So, by solving those equations simultaneously, you can basically calculate the critical parameters, and we can derive the specific values of the transition. First parameter can be the transition temperature, that is T Ni. So, we understand that the temperature at which the nematic phase becomes energetically favorable over the isotropic phase is this. So, this is the transition from isotropic to nematic. So, if you want the liquid crystal to behave like a nematic crystal, so you have to have this temperature. So, T Ni equal T star plus 2 b square divided by 9 AC. What is the critical order parameter here? The order parameter at the moment of the transition is basically 2b by 3c. Okay. Now, this equation basically indicates a first order transition, as the order basically jumps discontinuously from first 0, because when it was isotropic it was 0, when it is nematic or in the transition, the moment of transition to nematic, it is SC. So, there is a discontinuous jump from 0 to SC. So, now we will go to this theory, which is Meyer-Sope theory, that basically helps us explain the nematic ordering using the intermolecular transition. So, what is the nature of the molecular transition? The first one is anisotropic forces, something like the interactions, the van der Waals interactions, which are stronger along the long molecular axis due to the higher polarizability when you compare them with the short axis. Okay. So, this anisotropy basically creates a physical preference for the molecules to point in the same direction. So, what you get is basically parallel alignment of the molecules. So, the mean field can be introduced, a mean field potential can be introduced for a single molecule. So, in that case, the effective single molecule potential V, okay, for that, instead of calculating every intermolecular collision, we can treat one molecule as existing in an average field that is created in the presence of other molecules. Okay. So, with that you can calculate the potential. So, the potential V theta basically follows 3 rules. The first is its minimum at the director. So, the energy is basically lowest when the molecules aligns along with the liquid crystal director n cap. So, n cap, if you remember, that is basically the average direction. So, if one molecule is aligned along that n cap, it has got the minimum potential. Now, proportional to the order, okay, that is the second rule. So, the potential well is deep when the system is ordered, that means S is high, and it basically disappears when the crystal becomes disordered, that means S equals 0. And the third rule is that the potential basically treats up and down orientations at identical. So, this basically that is up down symmetry. So, it is like non-polar. So, with that the potential is basically defined by the second order Legendre polynomial. So, you can see V theta can be written as minus nu, or that is basically the interaction constant, okay, S 3 by 2 cos square theta minus half. Okay. So, as I mentioned, this nu is basically the interaction constant, that is roughly the magnitude of the thermal energy kBT and theta, and you will see this. So, we will do this again. So, where nu is basically the interaction constant, which is roughly the magnitude of the thermal energy, that is kBT, and this theta that you see in this equation, that is basically the angle between the individual long axis and the liquid crystal director, that is n cap, which can be seen here. So, the probability for the molecule orienting along the direction with polar angle theta can be written, or you can say it is governed by the Boltzmann's distribution function. So, you can write f of theta is e to the power minus V theta by kBT divided by integration from 0 to pi e to the power minus V theta by kBT into sin theta d theta. So, that also allows you to calculate the single molecule partition function capital Z, that is basically this one, okay, the one in the denominator. So, 0 to pi e to the power minus V theta by kBT into sin theta d theta. So, from the orientational distribution function, we can basically calculate the order parameter, that is S, that is 1 over Z into, you can bring in that value of B theta that we know, that is P2 cos theta, okay, into e to the power minus V theta by kBT into sin theta d theta. Okay. So, that can be further written into V So this part remains same. So minus v theta can be written as small nu s p2 theta. Okay. So that way you can basically express this order parameter. So this particular equation yields three possible states S1, S2 and S3, and the physical state is always the one that has got the lowest energy. So this also tells you the normalized temperature as tau, small tau, which is kBT divided by nu. That can help you simplify the calculations. So it also tells you about the free energy F that has got two parts, F equals U minus T E n. So U is basically the intermolecular interaction energy and E n is the entropy, right. So the interaction energy and the entropy of the system with n molecules can be given as interaction energy is nothing but half n then average of V. So that is basically half n small nu or small v square, okay, and E n is nothing but minus n kb average of ln f. Okay. So from this the total energy F basically balances the intermolecular interaction energy and the entropy. So this is basically obtained using equation 2, 3 and 4. So that is 2, 3 and 4, that basically gives you this one. So what you see here, you basically see that the phase stability condition T greater than equals T n I. So you have isotropic phase, that is S equals 0, and it has got the lowest energy and that is why it is stable. Okay. And for T less than T n I, that means the nematic phase where S is greater than equal to 0, that has got the lowest free energy. So this nematic stage is basically stable. So you need T less than equal to T n I for this one. So these are those three solutions of the order parameters that were described earlier, plotted as a function of normalized temperature small tau in this Mayer-Soap theory. So these are the solutions S1, okay. So that is S1 is always 0, S2 is this one and this is S3, okay. So here you see the normalized free energy F1, F2 and F3 for the three systems, okay. These are basically for the three order parameters that have been calculated. So with that, now we will discuss some properties of elastic properties of the liquid crystals. So we have learned that in ideal state the liquid crystal detector n cap is perfectly uniform in space, but in reality the liquid crystal detector n cap basically varies spatially due to confinements or external fields. So this spatial variation of the detector is also called the deformation of the detector. So such deformation basically forces the molecules out of parallel alignment and it costs some elastic energy. So when the spatial variation occurs over distance which are much larger or longer than the size of the molecule itself, a continuum theory can be basically used to describe those deformation. So the elastic energy is basically proportional to the square of the spatial variation rate, and this is the basis for describing the detector distortions in a liquid crystal device. So what is the key idea here? The detector deformation is basically leading to elastic restoring forces. Okay. So here you can see the elastic properties of the pneumatic liquid crystals. The first thing is a liquid crystal detector n cap or n can undergo three kind of fundamental spatial variations from its initial alignment. Okay. So these three fundamental forms of deformation can be characterized by how the detector is basically tilting with respect to its initial axis. So the initial axis is always maintained as the z axis, but after that how it is changing. So one is called splay mode, that is the radial tilt. So, what is the radial tilt? The director basically tilts outward along the radial direction. Okay. So, this is how it can tilt. Okay. So, it can be associated with splay elastic constant K11. The next one is called azimuthal tilt. So, here they are basically getting tilted in the azimuthal direction. So, there is a twist here basically. Okay. So, here you can see they are getting twisted. Okay. So, here it was along z, here it becomes completely along xy. So, they are basically moving in this direction. Okay. So, it is azimuthal tilt. So, the director tilts rotationally along the azimuthal direction phi. So, here you can see that. So, this you can associate with twist elastic constant K22. The next one is the bend mode. Okay. So, bending happens like this. This is called the axial tilt. So, here the director basically tilts as you move along the initial z axis. Okay. So, you basically move along the z axis, but then here it was all same, but here it gets tilted slightly this way and that way. So, that is called bend movement. So, you can associate bend elastic constant K33 with that. So, this 3 different modes are there. So, you can obtain the total elastic energy density that is required to deform the liquid crystal, which will come out as the sum of the energies from these 3 different modes, and this is known as the Ocean-Frank energy density equation. So, the elastic energy density equation, if F ELA, so that has got all these 3 coefficients. So, half K11 delta dot n square plus half K22 n dot delta cross with n. So, this is the curl of n whole square, because there is a twist here, and then you have half of K33 n cross with curl of n whole square. Okay. So, the first term, that is half K11 divergence of n whole square, that represents the splay energy. Okay. So, here the dou np by dou rho, or you can say the divergence of n is basically giving the spatial variation rate for the splay deformation. The second term is basically the twist energy. Okay. So, here half K22 n dot curl of n whole square, it represents twist energy. So, here you can calculate it as dou n phi divided by dou rho. Okay. So, that is basically this term, okay, which is n dot curl of n. So, this gives you the spatial variation rate for twist deformation. The last one, that is this term, half of K33 n cross curl of n, this represents whole square, this represents the band energy. So, you can do it like this, dou n p, or it can be n rho, okay, divided by dou z, okay, or you can write it as this term, which is n cross curl of n. This is the spatial bending rate for bend deformation. So, one is for twist, one is for bend. So, in typical liquid crystals, something like the 5 Cb that we have seen, the constants usually follow the hierarchy. So, you will see the band K33 is the largest one. So, that is the hardest to deform. Then splay, this one is the intermediate, but the twist K22 is the smallest. So, that means this is the easiest one to deform. So, they can always go from this to this kind of a form. Okay. So, you can see this is the easiest one to. Now, let us look into the elastic properties of the chlorosteric liquid crystals. So, chlorosteric liquid crystals are basically chiral molecules crystal. Okay. So, chirality versus achirality, you can understand. When I say achiral, these molecules basically possess reflection symmetry. That means, they look identical to their mirror image, just like a standard rod. If you take a mirror image, it will look exactly same. However, if you have twisted molecules, or chiral molecules, they will not have this reflection symmetry. They will basically differ from their mirror image. That means, you have right handedness and left handedness, which get swept when you see the reflections, just like they are behaving like screw. Something like CB15 looks like that. Okay. So, this is a chiral molecule, and that is the difference between this and this. So, if you take a mirror image of this, you will not get exactly the same molecule. So, in such case, how do you obtain? So, when you consider chiral molecules, the chirality term Q naught, that gets added up to the twist component of the elastic energy density. So, that gives you the generalized Ocean-Frank elastic energy equation. So, this new term gets added, which is coming from the chirality, right. So, for achiral molecules, that is Q0 is 0. So, that means the ground state is uniformly aligned. For chiral molecule, okay, this is non-zero. That means, the ground state forces a twisted configuration. Okay. So, when we talk about chlorosteric phase, that means, we are talking about the chiral nematic phase. Okay. So, here when you say chiral, this is now non-zero. So, the minimum free energy ground state will require the liquid crystal director to twist continuously in the space. So, here you can see how it changes. Okay. So, this is the pitch, you can say. So, it starts with this, then it slightly moves like this, then like this. Okay. Slowly it is getting moved, and finally, here it goes back to the same rotation. Okay. So, this is how you can say this is the x axis, this is the z axis, this is the y axis, and this is the entire length over which it gets back to its initial position. So, you can write nx is cos q naught z, and y will be sin q naught z, and nz is basically 0. So, the director twists around the helical axis, which is the z axis here. Okay. So, what you have obtained another thing, the helical pitch. So, when it is getting moved like this, there is a length over which, or you can say a distance along this helical axis, over which the director will basically getting a full 360 degree twist, or you can say it is getting twisted by 2 pi radians. So, here this is the one. Okay. So, you can correlate this with the chirality factor. So, Q naught. So, P naught is given as 2 pi by Q naught. And note that we have considered n cap and minus n cap to be physically equivalent. Okay. That means, the structural periodicity is basically here, it is P naught by 2. So, how do you engineer the pitch? Okay. That means, the chiral doping. So, in practice, the cholesteric liquid crystals are often manufactured by mixing a small amount of chiral dopant to the standard nematic host material. Okay. So, this is how you basically get the pitch of a mixture. So, you have P equals 1 over HTP into X. So, X is basically the concentration of the chiral dopant in a mixture. Okay. And you see this HTP is basically the helical twisting power. So, this is the constant that is determined by the chemical structure of the dopant and its interaction with the specific nematic host material. So, let us quickly see the elastic properties of this smectic liquid crystals. So, unlike the nematic one, the smectic liquid crystals, particularly this A type, they possess both orientational as well as partial positional ordering. That means, the molecules arrange themselves into distinct layers. So, layer dilatation, that means expanding or compressing these smectic layers will cost energy, while this makes them resistant to the thickness changes. So, layer dilatation energy comes from the fact that compressing or expanding these layers will cost energy, and the equation for the energy density in this case can be written as F layer, which is 1 over B divided by multiplied by d minus d naught over d naught whole square. Now, what is B? B is basically the Young's modulus for layer dilation, which is typically 10 to the power 6 to 10 to the power 7 joule per meter cube. So, which is much smaller, or you can say softer than the solid crystal. And then you have these parameters d and d naught. They are basically, d naught is basically the equilibrium layer thickness, and d is the actual layer thickness of this smectic layer. So, the deformation constraints, there is no twist, no bend rule. Okay. Let us see what is that. Because maintaining layer thickness is energetically preferred, because deformation will cost energy. So, the liquid crystal director cannot twist or bend. Therefore, only splay deformations are basically permitted in smectic A phase. So, you can just do this or this for the smectic A phase. So, here you can see that it basically shows deformation of the liquid crystal director and the smectic layers in the smectic A liquid crystal. So, in a slightly deformed smectic A case, the director field must specify or must satisfy a mathematical constant, that is curl of n equals 0. So, this mathematical property basically ensures that the twist, that is n dot curl of n, and the bend, which is n cross curl of n, these two terms from the Ocean-Frank energy, these two terms will become 0. So, in that case, the total elastic energy, that is F elastic of smectic A, because twist and bend both are forbidden. So, the total elastic energy density in the smectic A liquid crystal only will have the splay deformation and this layer dilatation term, these two terms. Okay. Now, for this smectic liquid crystals, let us see the phase transitions and the pitch divergence. For chiral liquid crystals, transitioning from isotropic to cholesteric and finally to smectic A phase. Okay. So, in smectic A, the pitch is infinite, right, because the twist is forbidden in smectic A phase. So, you can say that the structural pitch basically becomes infinitely long, that means it completely untwists. Okay. So, what is the pre-transitional phenomena? So, as the temperature drop towards the cholesteric to smectic A transition, you will see that the thermal fluctuations cause tiny localized patches of smectic A order to form temporarily within the cholesteric phase, and this basically results to cholesteric helix, where it begins to aggressively unwind, and that is why it is like a this kind of case. So, the helical pitch increases sharply as the temperature drops, eventually it diverges to infinite precisely at the transition temperature. So, here is a important slide that tells you about the properties of thermochromic liquid crystals. The diverging pitch near the phase transition is the fundamental mechanism behind thermochromic liquid crystals, that means the materials that can change color with temperature. The first property is the Bragg reflection. So, cholesteric liquid crystals basically selectively reflect light based on their pitch. So, the equation is like this: lambda equals n bar p, lambda is the wavelength of the reflected light, and n bar is the average refractive index of the crystal, and p is the helical pitch. So, what is the link between the temperature color here? Because p basically, that is the pitch, changes rapidly with the temperature near the smectic A transition region, the reflected lambda basically sweeps through the visible light spectrum. So, by mixing different cholesteric compounds to tune the transition temperature, one engineer can create highly sensitive color changing thermometers, okay, something like forehead thermometers or mood rings. Okay. So, with that we complete the basic properties of liquid crystals, and We will also look into some other important topics like liquid crystals, electromagnetic response, their anchoring effects, elastic deformations in the next lecture. If you have got any doubt regarding this lecture, you can drop an email to this email address mentioning the course name on the subject line. Thank you.